For the first exercise, they are asking you to find the frequency and period of a ball tied to a rope with an angular velocity of 60 revolutions per minute. This is all about converting the revolutions per minute of the angular speed to cycles over second, which is the unit of the frequency, hertz. So we know that 60 seconds equals 1 minute, and that a whole cycle of the ball is 60 revolutions. And with that, we can convert the angular speed and say that the frequency is equal to 1 hertz, and for the period, it's just as easy to divide 1 over the frequency, giving us a period of 1 second. The second exercise is asking for the speed of the tines of a tuning fork, with a frequency of 300 Hz and an amplitude of 2.2 mm, which is equal to 0.0022 meters, if the displacement is 1 mm. Well, knowing that the displacement doesn't really affect the frequency, we can easily use this formula, which would give us a total speed of 4.146 meters per second. The third exercise wants you to find the work and potential energy acquired by compressing a spring by 35 mm, which is equal to 0.035 meters, if its constant is 190 newtons over minute. First, to find the potential energy, we need to use this formula, and substitute to get a potential energy of 0.116 joules. Then, for the work, we have to find the force first, which is obtained by using this formula, giving us a total value of minus 6.65 newtons. Then, with the force already obtained, we shall just substitute the values in this formula to get the work, giving us a work of minus 0.222 newtons over square meter. For the fourth exercise, it is asking you to find the speed of a transversal wave along a wire with a mass of 0.5 kilograms and 0.5 meters long and a subjective tension of 100 newtons. First, we have to get the string linear density using this formula, giving us a linear density of 1 kilogram over meter. And with that, alongside with the force, we can use this formula to get the velocity of the wave, which is 10 meters per second. Next, in the fifth exercise, it is giving you a mass of a 4-meter rope with a tensile strength of 300 newtons and a wave speed of 150 meters per second in order for us to find the mass. We could use the string linear density formula in order to clear out for the mass, but we would first have to use the velocity formula and clear out for the linear density because we don't know how much it is. By doing so, we will get a linear density of 0.013 kilograms over meter. So now that we have the string linear density, we can work with its formula and clear out for the mass, giving us a mass of 0.053 kilograms. Number 6 was the most complex one for me, as it is asking you to get the time that sound takes to travel through a piece of copper rod of 2.5 meters long, knowing that copper's density is 8800 kilograms over meter cubic, and the modulus density is 1.17 times 10 elevated by 11 pascals. So for this, you'll have to get the velocity by using this formula, because we'll need it later, giving us a velocity of 3046.29 meters per second. So we need the speed because we don't have a specific formula for time on this topic, so we can use the regular velocity formula, being distance over time, and we would just have to clear out for the time, giving us the result of a travel time of 0.00068 seconds. The seventh one is all about using logarithmic rules and clearing out, and it is asking you to find out the intensity of the sound in watts over square meter, so you can use the decibel scale formula to clear out for the intensity, as you already know the value of the minimum intensity humans can hear, which is 1 times 10 elevated by minus 12 watts over square meter, and the 55 decibels, which are equal to 5.5 bells. So with that info, we can use the logarithmic rules to be able to clear out all of the values in the equation and finally clearing out for I, giving us an intensity of 0.0000031 watts over square meter. The last two exercises, both 8 and 9, are super simple. First, the 8th one is asking you to get the frequency at which you hear a car when getting closer to you and when moving away from you. With the car going at 60 km per hour and producing a frequency of 560 Hz. First, we have to convert the 60 km per hour to meters per second, which is equal to 16.66 meters per second. And then we have to use this formula, knowing that the average speed of sound in air is 343 meters per second. and just change the sign to positive or negative whenever the car is approaching or moving away from you. So with that, we can conclude that you'll hear a frequency of 558.60 Hz when approaching and 534.05 Hz when moving away. The ninth and last exercise is exactly the same exercise as the previous one, but now we're talking about a subway that has a speed of 72 km per hour, and its horn produces a frequency of 330 Hz, and it's also asking at which frequencies you would hear the subway if it was approaching to you and moving away, guessing that you aren't moving. Same as before, we have to convert the 72 km per hour to meters over second, which equals to 20 meters over second. So then, we just use the same formula as the previous exercise, changing the symbols to positive or negative if the subway is moving away or approaching accordingly, giving us a frequency of 311.81 Hz when moving away, and a frequency of 350.43 Hz when approaching.